All right, welcome back, College Chem. Today we're going to talk about a little bit more about gases, and specifically we're going to use what we call the ideal gas law. So this will just kind of help you get started on this handout 5.5. We also have a handout 5.6 that I think we're probably going to end up collecting from you. But let me just give you kind of a few details on this handout so that you can work on it, okay? The first part of this handout starts out with Avogadro's law. And here's the idea is that we're looking at moles of a gas. We call this N1, a certain number of moles of a gas, and N2. If we were to look at sort of the amount of particles here and the amount of particles there, our number of moles goes up. And assuming that the pressure is constant and the temperature constant, if you were to compare the volume in the first container of the gas to the second container, I think you would see pretty quickly that by increasing the number of particles, you're going to increase the volume. That's assuming that pressure is constant and temperature is constant. And that makes sense. You put more air in a balloon, the balloon's going to blow up. You put more air in a tire, the tire is going to get bigger in terms of volume. So that's Avogadro's law, is that as the number of particles increases, your volume increases, okay? All right, now trying to put this all together, if we look at this model 2, I want you to notice that there's three gases we're comparing. We're comparing the first gas, helium, and we're comparing that to nitrogen, N2, and O2. And here's what we're doing. We're looking at 1 mole of each gas. So if you look closely here with the numbers, we've got a mole of each. So a mole of helium, a mole of nitrogen, and a mole of oxygen. And we're going to keep them at what we call standard temperature pressure. And that's what the conditions are here. We've got 1 atmosphere, which is equal to 760 torrs or millimeters of mercury. We do that for all of them. And then our temperature is at 0 degrees Celsius, which is in Kelvin 273. This is STP conditions. So if we take a mole of gas at standard temperature pressure, STP conditions, here's what we would notice. That gas is going to take up a certain amount of space, 22.4 liters. And it doesn't matter which gas we're talking about, all of these gases would take up 22.4 liters of space. In fact, that is something you want to catch. One of the big points of this handout is 1 mole of any gas at standard temperature pressure is equal to 22.4 liters. And we'll come back to that a little bit later in the unit with gas stoichiometry. That's kind of a really important number for you to remember. 1 mole of any gas at STP, standard temperature pressure, is 22.4 liters, okay? And it doesn't matter what the gas is, okay? But here's also what I want you to look at. I want you to look at now a little bit the last 2 parts of this chart, and that is mass and density, okay? So first of all, you should know and should remember that density is the ratio of mass and volume, okay? And notice here, even though we just kind of went through and talked about how all of these gases have the same number of moles, pressure, temperature, and volume, what you're going to notice here is that their densities are different, okay? Well, how could that be true? If they have the same volume, 22.4 liters, how in the world would their densities be different? Well, think about what's in the equation. If their volume's all the same, it must be that our masses are different. And if you think about it, 1 mole of helium has a mass of 4.003 grams, and 1 mole of nitrogen has a mass of 28.02, and 1 mole of oxygen has a different mass of 32.00 grams. So first thing to catch here is any gas at STP, that's again 273 Kelvin and 1 atmosphere. To calculate the density, you assume 1 mole. This is really the easiest way to do it. Assume 1 mole, and all you have to do is you have to take the molar mass and divide it by this 22.4 liters, and you can easily find the density of that gas. So for instance, for oxygen, we look at the molar mass of oxygen, remember it's 32.00 grams. If we were to divide that by 22.4 liters, and then turn around and punch that into a calculator, 32 divided by 22.4, we're going to get 1.43, and the units are grams per liter. That's how we get that number of 1.43 grams per liter. If we did the same thing over here to helium, all we would have to do is take the molar mass of helium, 4.003, divide it by 22.4, and you get 0.179 grams per liter. So it's really easy to find the density of any gas at STP. You just make the assumption you have a mole of it, use the molar mass divided by the 22.4 liters, and there you go. Now, if the conditions are different, they're not at STP, it's going to be a little more complicated. I'll show you that here in a couple minutes, but I wanted you to see how we calculate the density of a gas at STP. All right, moving on a little bit further down the handout. Here is big picture. Here's what we're looking at. We have a new equation. This is called PIVNERT, or I like to call it PIVNERT. And it's what we call the ideal gas law. And it is the relationship between the four variables that we deal with gases. We have four variables. We have pressure, volume, number of moles, and temperature. In fact, if I were to move all four of those to one side of my equation and kind of set up a proportion, we would say that pressure times volume divided by number of moles times temperature is equal to this R. Okay, what is R? R is what we call the gas constant. It's called the universal gas constant. And it is something that we're going to use. It's 0.0821 is the value we tend to use in college chem. And in order for you to use this R value, you're going to have to be in some specific units. For pressure, we use atmospheres. For volume, we're going to have to use liters. For number of moles, we're going to use MOL. And then for temperature, we're going to have to be in Kelvin. These are the units, and that's typically how the R value is given, is 0.0821 liters times atmospheres over moles times Kelvin. And if you look closely there, you can actually come up with that equation pretty easily if you know the units which are given as the R value. What does this excuse me, mean? It means no matter what the conditions are of a gas, if you have a pressure and a volume and a number of moles and a temperature, that ratio of those four variables are always going to be equal to this universal gas constant. So if pressure goes up, something else has to change to make it always equal to that 0.0821 number. So remember, like pressure goes up, volume must go down, or if pressure goes up, it's because temperature or number of moles went up, and so on. How will we use this equation? Well, the most common way to use that equation is we give you all of the variables except for one of them, and you have to solve for the unknown. So it's pretty straightforward solving. You just have to make sure you're in correct units. So if we gave you a temperature in Celsius, again, make sure you go to Kelvin. And you might have, for instance, grams and have to convert that to moles so that you can plug it in for N and so on. But this equation is a really important equation called the ideal gas law. And it's true of all gases, doesn't matter what the gases are. That's the relationship between those variables, okay? Let me show you one other equation, and I want to show you how we get to it. So this is a variation of the ideal gas law. So remember the ideal gas law, PV equals nRT. I want to show you how we can come up with another equation that's going to help us. And here's what you want to think about is, you know that molar mass, I'm going to use capital M, is really the relationship between the number of grams and the number of moles of a substance. It's grams per mole. Well, that would be mass per mole. That is M over N, mass for M, N for number of moles, right? The other equation I want you to look at for a second is density. Density is mass over volume. We're going to use these two relationships to sort of rearrange and come up with a different equation that's going to be helpful in this unit. So if I do a little bit of crisscross, I kind of like to do cross multiplication, but as it turns out, these two variables really flip-flop with each other if I want to get N by itself. So really, number of moles is the same thing as mass over molar mass. And you should be able to figure that out. But that is what, if I wanted to get N by itself, that's what we would end up with. So I'm going to use this relationship, and I'm going to go back to my PV equals nRT equation. And instead of using N, I'm actually going to plug in little m over big M, so mass over molar mass. So I'm going to go with PV is equal to mass over molar mass times RT, plugging that in. I don't like having a fraction there, so I'm going to multiply both sides by capital M. So I'm going to get PVM is equal to mass times RT. Okay. Now, I want to get volume to the other side. Why do I want to get volume to the other side? Is because I want to look at this relationship with density. So if I divide both sides by volume, volume is going to go away on the left, and I get PM is equal to MRT divided by V. Now, you should know this from math class, but I can just pull out M over V. So if I treat it like I'm just dividing mass, it really is the same thing. If you don't believe me, talk to your math teachers. But look back at what mass over volume is. It's equal to density. So we have a new equation here that I can rearrange for. PM is equal to DRT. Why we care about this equation is because when we're dealing with gases and we want to know something about density, or we could potentially even try to find the unknown gas's molar mass, this equation becomes really helpful. And it's just a derivation of PV equals nRT when we go through and sub in some mass and molar mass and mass and volume for density and so on. So that's going to show up if you look at, scroll down the page here. If you look at question number 6, let me just run through this one with you here. We have this PM equals DRT equation. I call this the DIRT equation. So if you hear us referring to it, that's what we're dealing with. It says use the variation of the ideal gas law to calculate the density. So we're going to calculate density of 52 grams of nitrogen at 298 Kelvin, 0.78 atmospheres. I'm just going to cut to the chase here. PM equals DRT. We're going to get D by itself. So we're going to divide both sides by RT. And that's what density is equal to. So D is equal to PM. So I take my pressure. I do have to be in atmospheres because my R value that I'm using is that 0.0821 liter atmospheres over mole Kelvin. My molar mass, if you think about it, for nitrogen, it's 28.02 grams per mole. That's just something I can use my periodic table to figure out. And then the R value is 0.0821. And then my temperature is 298 Kelvin. So I punch all that into a calculator, 0.78 times 28.02 divided by 0.0821 divided by 298. And you're going to get, we're only going 2 sig figs here, 0.89. What are the units? Well, we're dealing with gases, so it's grams per liter. And you could probably figure that out. If we went through and crossed out and kind of looked at all the variables, it should turn out to be grams per liter. This is how you deal with density of gases when you're not at standard temperature pressure, okay? Again, we are assuming, in some ways, we are assuming that we have 1 mole because we're using the molar mass for this, okay? So that is one of the very helpful variations of our PV equals nRT equation, is using what we call the DIRT equation. PM is equal to DRT. How else could you use that equation? Well, use this equation, if I actually knew the density of a gas, but I didn't know what the gas was, I could rearrange this, divide both sides by pressure, and I would get molar mass by itself, and I could do dRT divided by P, solve for molar mass, and then maybe you have a list of choices of gases. We've got a couple problems I think you're going to do that for. But I think this is enough. This should get you started on handout 5.6, and you should be able to work through also handout 5.5.